Hello everybody, in this video I'll go over the second part of section 4.3, which is concavity. I'll go over some definitions, then we'll do examples, and then at the end I'll sketch the graph of some functions given conditions on the first and second derivatives, okay? So even if we don't formally know what concavity is, mathematically speaking, we all understand that this is the graph of a concave up function and this is concave down, okay? Now, if we want to formally define this using calculus, what do? We think in terms of the derivative, of course. So if I draw my tangent lines, for example, if I say that this is the graph of f, this is the graph of f, then if I draw my tangent line here, I get that f prime is less than 0. Then here, my tangent line is horizontal, so I know that the derivative is equal to 0. And then after that, if I draw my tangent line, I'm going to get something with positive slope. So I know that my derivative is going from negative to 0 to positive. So it is safe to say that my derivative is increasing, right? So I'm just going to tell you that. I'm going to say, okay, if f is concave up, like in this graph, then f prime increases, as we saw. But then my question is, if I know that a function increases, what happens to its derivative, right? So if a function is concave up, then the derivative increases, meaning the derivative of that function is positive, meaning the derivative of my derivative is positive, meaning the derivative of my function, so f double prime, it's greater than 0. Okay, so we can say that, and we can turn this into a definition. If it's concave up, well, I'm going to say if it's concave up, then that tells me that my function, the derivative increases, and that tells me that then the second derivative is positive, okay? Now, if we do the same thing now, but for my concave down part, so this is concave up. So if now we do it for the concave down part, then I know that if I draw here, I draw my tangent line, I get something positive. Then here, I get something equal to 0. And then here, my slope is negative, meaning the derivative is less than 0. Okay, hold on, less than 0. So in this case, it's the opposite is happening, right? So I know that, how bad is this? I know that now the opposite is happening, okay? So now I know that if it's not concave up, but down, so if it's concave down, and now I know that if I look at what's happening to the derivative, I see that the derivative is decreasing. So the derivative is now decreasing. Therefore, the derivative of the derivative has to be negative, okay? The derivative of the derivative, it's negative. One more time, I know that if a function decreases, then its derivative is less than 0. In this case, the function that it's decreasing is a derivative. Therefore, its derivative will be less than 0, meaning the second derivative of the original function, okay? Perfect. Something else that we see here is that, I don't know if you noticed this, but if you think about it here, we're saying that this whole thing is concave up. However, the derivative, it's less than 0. The derivative is greater than 0. So that tells me that I can have a function increasing concave up or decreasing concave up. Same thing here. It can increase concave down. It can decrease concave down, okay? So by that I mean that you have 4 different possibilities, okay? So you have 4 different possibilities. You have, say, for example, you have number 1, what happens if f prime is greater than 0 and if double prime is also greater than 0? What happens if f prime is greater than 0 but f double prime is less than 0? What happens if f prime is less than 0 but f double prime is greater than 0? And then finally, what happens if f prime is less than 0 but f double prime is also less than 0? Meaning the first one, the function increases concave up. So if a function increases concave up, then it increases concave up, so it'll look something like that. Okay? Now, number two, the derivative is positive, the second derivative is negative, so it increases concave down. So if it increases concave down, then it will look something like that. Okay? Then for the third one, the derivative is negative, meaning it decreases. So here I know that so I was saying here it increases concave up, here it increases concave down, here it decreases concave up. So if it decreases concave up, then it looks something like that, right? Decreasing concave up. And then the last one, I know that it decreases concave down. So if it decreases concave down, it has to look something like that, okay? So these are the only four possibilities we have when it comes to the behavior of a graph given the information we have from the first and second derivatives, okay? So in my previous video, where we were talking about critical numbers and how if a function had a local max or local min, it came from a critical number, meaning that was the place where the first derivative, the sign of the first derivative changed. Now for the second derivative, we'll have something very similar, okay? But in this case, instead of local max, local mean, we're going to have inflection points, okay? So now an inflection point is that point where the concavity of the function changes. So we know that if it's concave up and then it changes to concave down, then that's an inflection point. And if it goes from down to up, then that's an inflection point. And it'll look something like this, okay? It'll look something like this. So I look at my graph, and this is again the graph of f. This is the graph of f. I have some function f. And if you look at it, it looks like it looks concave down from here, like all the way here. So it's concave down. And then from here on, it's concave up. Right? So that point where the concavity changes, that is my inflection point. So this is my inflection point. It is a point. They have x and y coordinate, okay? Now, so just by looking at it, if you wanted to have a way of determining whether a point is an inflection point without knowing the graph of the function, then obviously it's the place where the concavity changes. In other words, it's the place where the derivative goes, the second derivative goes from from negative to positive, or vice versa, from positive to negative, okay? So one more time. So notice that an inflection point is that place where the second derivative goes from positive to negative or negative to positive. Therefore, it has to, at that point, at that value, the second derivative has to be either 0 or does not exist, and then it has to live in the domain of the function. I'm going to write it down. So what I'm saying is that now we know that this number d is in the domain of f, and on top of that, f double prime of d is equal to 0 or does not exist. Okay? Beautiful. So let's do an example, okay? Now I want to find the intervals where f of x equal to negative x cubed minus 2x squared plus 5x plus 10. It's concave up or down, and any inflection points. We're going to do exactly what we did for critical numbers on local max, local mean, but for the second derivative, okay? So now my step one is, find the second derivative. Okay, so we find the second derivative. We take that second derivative, we set it equal to 0, okay? We see if, we make sure that that number we get, it's in the domain of the function, which in this case we have a polynomial, so yes. But we don't know if we get an inflection point until we look at the sign of the second derivative. One more time, if the sign of the second derivative changes from positive to negative at this candidate for inflection point, then we call it an inflection point. Okay, so let's do it. So of course, I have to get the second derivative. The only way you can get to the second derivative is by computing the first derivative first. So f prime of x is equal to negative 3x squared minus 4x plus 5. Now I take the second derivative and I get negative 6x minus 4, right? And this is equal to 0, well, if and only if negative 6x is equal to 4, and then x is equal to negative 2/3, negative 2/3. Okay, perfect. So now we have that, And then the next step is just to look at the sign of the derivative, the second derivative, before and after negative 2/3. So step 2. Now step 2, look at sign of f double prime in between those candidates for inflection points and it is continuous. Again, in this case, we have a beautiful polynomial. So I'm going to look at the sign of f double prime before and after negative 2/3. So before and after negative 2/3. In other words, I make my little table. So I go from negative infinity to negative 2/3, and then from negative 2/3 all the way to infinity. And then, as we did before, find the test value, plug it into a second derivative, you get something positive, the function is concave up. You get something negative, the function is concave down. So test value, sign of f double prime, and then what does the sign of f double prime tell me about my function? Okay. All right. Okay. So say, for example, if I need something less than or in between negative infinity and negative 2/3, I'm going to take negative 1. Okay? So if I do f double prime of negative 1, I get 2. And that is positive. Therefore, my function f, it's concave up. It's concave up. Okay? Now, if I substitute something in between, take pink. If I substitute a number greater than negative 2/3, I'm going to take 0. If I substitute 0, then I get negative 4, which is negative. So 0 is a negative number, therefore it is concave down. So that tells me that since the sign of the second derivative changes at negative 2/3, then an inflection point. So then that tells me that negative 2/3, my function f, the original function, evaluated at negative 2/3, it's an inflection point. It's inflection point of f. Okay? So then I get that this is negative 2/3, and if I evaluate my function one more time, the second derivative tells me that my function has an inflection point at negative 2/3, my function evaluated at 2/3, meaning this function, okay? The original function, this is the one that I have to use in order to find the actual point. So when I substitute negative 2/3 into the function, I get 6.074. That's what I get. Perfect. Okay. So let's start this problem. In this case, we have the graph of the derivative of the function, and we have to use the graph of the derivative of the function f to determine the intervals where the function f is concave up and concave down. Okay? So we have to go back to the definition of concavity, and we know that whenever the derivative increases, the function is concave up. Whenever the derivative decreases, the function is concave down. Okay? So I look at this graph and I go, okay, fine. I see that my functions, I'm going to assume here this keeps going. Okay. So I know that my function f prime, it increases from negative infinity all the way to negative 2, right? So we know that it increases there. So f prime increases. So if the derivative increases, then we know that the function is concave up. So that tells me that f, it's concave up. Okay? And then here at negative 2, the function starts to decrease all the way to 2. So from here all the way to here, the function decreases. So then from negative 2 all the way to 2, f prime decreases. And if f prime decreases, then we know that f, it's concave down. And then from 2 on, we see that from 2 on, the function increases, the derivative increases. So one more time, from 2 on, we see that f prime increases. Since it increases, then we know that the actual function f, it's concave up, okay? All right, so then f, it's concave up. Perfect. Now, there's one more piece of information that we can get from this graph, and it is the inflection points. So we know that whenever I go from concave up to concave down, or concave down to concave up, I have an inflection point, okay? Is that clear? So then if I look at this, I see that the concavity changes here, and concavity changes here. Now, this is the graph of the derivative, so I don't know what f is, okay? So the only thing I can do is say, okay, this graph, so then f has inflection points at, well, -2, whatever the function f is, evaluate at -2, and, well, 2, and whatever the function is evaluated at 2. Okay? Perfect. Thank you for watching again, and I'll see you next time. Bye-bye.